Okay, I think we can start. Thank you everyone for joining one more lecture of our computer architecture course. Today, lecture 23, we are going to talk about SIMD processors and GPUs. As I announced yesterday, this material is not going to be part of the exam tomorrow, but it's definitely good for you to attend this lecture or to watch it later, because we are going to talk about one of the most important parallel processing paradigms in this lecture. So as you can see on the screen, the agenda for today is, first of all, we will talk about SIMD processing. We are going to define SIMD processing in a theoretical way, and we will talk about the different approaches to SIMD processing, let's say classic approaches to SIMD processing that are vector and array processors. And after that, and after introducing as well what are the existing SIMD extensions in current CPUs, mostly, we will also talk about the architecture of graphic processing units. As you will see, they are essentially SIMD processors internally. A couple of recommended readings that are important for this lecture. The first one is about the MMX technology. This paper published in IEEE Micro 1996 is like a very seminal work in the sense of incorporating SIMD extensions to regular CPUs, x86 CPUs, and we are actually going to use this paper today to give you an example about MMX, and then also let's say a summary paper that explains the NVIDIA Tesla architecture, which was the first compute-capable architecture of NVIDIA. Yeah, so let's start the lecture. Today, we are going to talk about how to exploit data parallelism, because SIMD processors and GPUs are both good at exploiting data parallelism, and they are especially good at exploiting regular data parallelism, even though we are also going to see the ways that they can use to explore, to also exploit, irregular or more irregular parallelism as well. SIMD is one of the classes of computers that we can find in the classic Flynn's taxonomy of computers that probably most of you, if not all, are familiar with. The first one is in this taxonomy of computers is SISD, single instruction, single data, where a single instruction operates on a single data element. This the easiest example here is whatever single core processor that you may think about. It will probably be running a single thread of execution and will be operating on input data sequentially, right? Data by data. The second class in this taxonomy of computers is SIMD, which is the topic that we covered today. Single instruction operates on multiple data. And as I said before, here we are going to distinguish between two main types of processors, array processors and vector processors. The third class is MISD, multiple instructions operate on single data element. It's probably a not so common form of computer these days, but there are, let's say, close forms to MISD, for example, systolic arrays or streaming processors. And finally, we have MIMD, multiple instructions operate on multiple data elements or multiple instruction streams. And we have good examples as well in today's systems with multiprocessors or multi-threaded processors. This is the paper from Michael Flynn, Very High-Speed Computing Systems, and it's also a good and recommended reading from today's lecture. But let's take a look at some graphs, some figures from the paper itself. This is the MISD example from Flynn. Here, you can identify the data storage where all data is stored, and here we start from here we start feeding the execution units. As you can see, a sequence of execution units, or kind of a pipeline of execution units that are receiving instructions from some instruction storage, maybe kind of an instruction cache or an instruction memory. But as you can see, it follows the idea of multiple instructions that are executed by execution unit 1, 2, and so on, operating on a single piece of data that is coming through this source data stream. Probably these execution units on a real system might be pipeline, which enables some parallelism internally, but conceptually, from the theoretical point of view, as you see, the execution units are operating on a single data element that follows the whole flow. And this is kind of similar to a systolic array, and we can consider it kind of a generalized systolic array. By the way, I assume that you guys are familiar with systolic arrays, but if you are not, I think that the very good recommendation is this lecture from Professor Mutlu delivered in the past spring semester about systolic arrays. And we can also take a look at the example from Flynn for the SIMD architecture. Notice the difference with respect to the MISD example that we showed before. Here we have an instruction storage, and we have an instruction unit that is fetching instructions from this instruction storage and distributing these instructions to some execution units. And as you see, all the execution units have access by themselves to the operand storage. This is different from the MISD machine, because in the MISD machine, the data is coming from the same place, so it's input to one processing element, and then it propagates after that processing element or execution unit. While here is the instruction that is broadcast to all the execution units, and each execution unit has access to their own operands. So this is more similar to an array processor, which is one of the types of SIMD processors that we are going to explain today. So let's focus on them. Array processors and vector processors for a start, and after that, we will talk about GPUs. As I said in the beginning, SIMD processors are good at exploiting data parallelism. And what this means is that concurrency, or the simultaneous execution from multiple processors, arises from performing the same operation on different pieces of data. It's essentially the example that we have seen before from Flynn's paper. There we have multiple processing elements, and each of the processing elements is operating on a piece of data that is coming from the operand storage. That's a pattern that we can find, or a potential pattern that we can find in many real-world workloads, like, for example, the dot product of two vectors, where each of the vectors is composed by multiple elements, maybe hundreds or thousands of elements, and different execution units are going to operate on specific elements of those vectors in order to exploit the data parallelism. Notice that this is different from other types of concurrency. For example, data flow. In data flow execution, concurrency arises from executing different operations in parallel. So it's more exploiting task level parallelism instead of data level parallelism. And it's also different, SIMD is also different from thread or control parallelism, where concurrency arises from executing different threads of control in parallel. If you think about the multi-core machine, for example, there you will have multiple execution threads running on the cores, and each of the threads can be executing a completely different program and operating on completely different data. SIMD exploits operation level parallelism on different data. So this is a way of exploiting instruction level parallelism, but the instruction is the same instruction for all the execution units and all the data elements. So again, SIMD processing consists of a single instruction operating on multiple data elements, and this may happen in two different ways, or a combination of both, in time or in space. Let's see how. For now, let's assume that we have multiple processing elements, or PEs, or execution units, as we have just seen before, and these execution units will execute the same instruction at the same time on multiple data elements. Regarding the time-space duality, we distinguish between array processors, where an instruction operates on multiple data elements at the same time using different spaces. So what this means is that at the same time, we have several processing elements, and all these processing elements execute the same instruction at the same time. If one cycle later the instruction changes, it changes for all the processing elements. So as you see, the parallelism here happens in the space, right? Because all processing elements execute the same instruction at the same time. While in the vector processor, the instruction operates on multiple data elements in consecutive time steps using the same space. Imagine that we have a single processing element, but this single processing element is pipeline. If it's pipeline, what it means is that it can start operating on one of the multiple data elements every cycle, right? So, and after a few cycles, we will have several of these data elements in the pipeline being operated on, right? So if you think about the vector processor, you will see that we are using the same space, a single space, but the parallelism is being exploited in consecutive time steps, because the multiple data elements on which the same instruction is operated are coming one by one to the pipeline and to the execution unit. By the way, where are these data coming from? Where are these data elements coming from? In general, they will come from memory, but when it comes to feeding the execution units, we are going to talk about vector data registers. In the end, one vector register is just like a vector of registers, where each register has a certain width, for example, m bits, let's say 32 bits, 64 bits, and we have several of them. And all of them form a vector, and this vector is in charge of storing the data that will be sent to the execution units. You can see somehow like a representation here of the, each of these is an individual register, m bit wide, and all these registers here compose vector register 0. This is vector register 1, vector register 2, and so on. And as you see, the processing element has access to the contents of vector register 0, vector register 1, performs some operation, let's say an addition, element-wise addition, and stores the result in the vector register V2. Now let's go back to the idea of array processors and vector processors. Let's let's learn how to distinguish them based on a simple example. Notice that here on the left-hand side, we have our first SIMD program. It's a very simple instruction stream, but where you can already identify basic instructions like load, add, mul, and store. And you can also identify here their vector registers, right? In this particular example, we are using only one vector register called BR. So the first instruction, load instruction, accesses four elements from array A in memory, and these 4 elements are stored into the vector register. So we assume now that we know now that the vector register has 4 registers, right? Next, we perform this addition. With this addition, in the end, what we are doing is incrementing each of the registers in the vector register. Then we multiply by 2 each of these elements, and finally we store in the same positions of the array A. Now, at the right-hand side, you can see the array processor and the vector processor. As you can notice, the array processor is composed by homogeneous processing elements. All these P0, 1, 2, and 3 are exactly the same. However, on the vector processor, we have different units. Some of these units are specialized on different operations or different instructions. Here we see load, add, mul, and store. How are we going to execute this program for the 4 data elements that we want to operate on? In the array processor, the first thing to do is to load these 4 elements, right? Executing the vector load instruction. Then in the next cycle, after we have the data in the vector register, we can execute the addition. We add 1 to each of these 4 elements. Then we multiply by 2, and finally, we store in the same memory positions. On the other hand, for the vector processor, notice that we only have a single load instruction, unit. So what that means is we can fetch one value, one element of array A every cycle. So in the first cycle, we load element A0, second cycle element A1, and the third cycle element A2. But notice as well that at the same time, we can start the execution on the other units. Right after the load, we have to execute the vector add. So because the only element that we already have in vector registers is element A0, we can start executing on element A0, executing this addition on element A0. And one cycle later, we can do it for element A1. And then that's the same for the multiplication. So as you see, the instructions that are dependent on each other can start the execution when the final result of the previous instruction is ready, right? Notice that we have a data dependence here. And then execution continues. At some point, we have all 4 elements in vector registers, and we just need to wait until the rest of instructions finish the execution. As you can see here, we are operating on different data elements, but executing the same instruction at the same time. So every single cycle, we have a single instruction executing on these 4 homogeneous processing elements, while here in the vector processor, at the same time, we have different instructions being executed on the different processing elements, because in this case, the processing elements are more specialized. So this is what we call the time-space duality, right? So at the same time, in the array processor, we have different operations in the same space, while in the vector processor, we have the same operation in the same space. Okay, I hope that this distinction between array and vector processors is more or less clear. Don't hesitate to let me know if you have any questions. Also, if you guys, Joao, Luis, if you see any questions in YouTube, please feel free to stop me and ask them. Okay, so I think that we are understanding what this paradigm is about, SIMD processing. But let's make sure that we have differentiated it already from data flow execution, from multiprocessors as well. Let's distinguish it a little bit more from other execution paradigms. You guys might be familiar as well with VLIW, vector very long instruction word. It's a different paradigm where multiple independent operations are packed together into a long instruction. This is the work of the compiler that will analyze the program that the programmer has written, and will try to generate these long instructions that, as you can see, are composed by several different instructions that may execute even on different processing elements. But notice that the point here is that these instructions are independent of each other. So that's why they can be executed in parallel. This is a nice way of trying to exploit instruction level parallelism. But as you see, what it really tries to parallelize is the execution of different instructions that probably are operating on different data as well. However, in the case of SIMD processing, or at least in the case of array processors, because that's the example that we have here in the slide, this is an array processor with different processing elements that are, let's say, homogeneous. So here, it's actually the other way around. Instead of having a long instruction with multiple small instructions, we have one single instruction, and this single instruction is executed on the different data elements that are accessed by the different processing elements. If you want a refresher on VLIW, I can also recommend you this lecture from Professor Mutlu, also from spring 2021. Okay, so now that we more or less understand the definition of vector processors, let's talk more about them. SIMD processors, including array and vector processors. We are going to focus for now on vector processors, just as an example of SIMD processors. But I would say that most of the observations that we are going to make for vector processors also apply to array processors and GPUs as well. So let's start with the most basic definition here. A vector is a one-dimensional array of numbers. That's something that you all know, and it's very common that real-world programs, real-world workloads operate on vectors, right? So we are going to use today this simple code as a running example. Notice that this is a purely sequential code to be executed on a SysD machine, instruction by instruction, data element by data element. But in this case, what we have is a for loop, 50 iterations, And here we are essentially reading two elements from memory, elements from arrays A and B, adding them, dividing by 2, and storing the result in the corresponding element of array C. For a vector processor is a processor where these instructions operate on vectors rather than a scalar value. So as you see here in the sequential program, we are operating on scalar processors, where in the vector processor, we will have the ability of operating on all these 50 elements at the same time. That's essentially the idea. But there are some basic requirements. We need vector registers. We have introduced them already. These vector registers or vectors of registers is where we are going to load the input operands and the registers that will contain the output operands that we will later store in memory. We also need to define what's the length of the vector, because that's probably going to be a limitation that the hardware itself is going to impose. How many processing elements you have, how many processing elements you can use at the same time. If you think about an array processor where you have, in the example we saw before, we had four processing elements, that could be our vector length, right? And we would be executing vector instructions for every 4 elements. But maybe we can also have like an intermediate, let's say, software layer, and we could define a vector length, let's say, longer, like for example 50, right? And how are we going to execute these? How are we going to operate on these 50 elements using 4 processing elements? We will go 4 by 4, right? So if we have 40, we will need 10 iterations, right? We will need 10 cycles to input all the operands to the processing elements and finish the execution sometime later. And another thing or another type of register that we will need in vector processors is the vector stride register, which is going to define the way that we access memory. In the end, we are thinking about a very basic, very simple example like this one, where you see that all consecutive elements of arrays A, B, and C are going to be accessed, but there may be access patterns that are not like that. That maybe we will first access element 0, then we will access element 9, then later we will access element 18, and so on. So we may have, for example, strided access patterns where the distance between 2 consecutive elements, so 2 elements accessed back to back, one after the other, is more than 1. So that's what we normally call the stride. And in order to better understand the definition of a stride, let's take a look at a matrix multiplication example. As you know, matrices are 2-dimensional data structures, but they are stored in memory in a row major order. So if you look at these 2 matrices that maybe we are going to use for a matrix multiplication, this array, so this matrix A will be stored row by row, right? So what that means is that these 6 elements will go right before the next 6 elements that correspond to the next row. However, in the case of matrix B, I mean, it's going to be stored in the same way. These 10 elements of the first row will be stored in memory before these 10 elements of the second row, right? But then the point that stride comes when we need to access these matrices. And if you execute the matrix multiplication of A and B to obtain the output matrix C, what you will notice is that the way we access the elements in array A is horizontally, right? So first dot product to execute for this matrix multiplication is the dot product of this row A0 and this column B0. So if we have to access these 6 elements, we will go linearly in memory. And the distance between 2 consecutive accesses is only 1. However, in the case of B0, the distance between 2 consecutive elements of the same column is 10, actually. And this 10 is the stride. So here you can see it more clearly. Here on the right-hand side, you see the 6 elements from A However, the 6 elements from B are at a distance of 10, right? So first element to be accessed is this one here, and the next one is this one here. So as you know, we will read this element, then multiply by this element here. Next, we read this element, multiply by this element here, and accumulate. And as I said, the stride in the case of the matrix B is a stride of 10. So this is the definition of the stride. And when it comes for vector load and vector store instructions to access memory, to read or write data, these vector instructions, these load and store instructions, need to know what's the stride to access memory, right? If the stride is 1, the vector load instruction will read these 6 elements. If the stride is 10, the vector load instruction will read these 6 elements here. Okay, so a vector instruction performs an operation on each element in consecutive cycles. Vector functional units are or can be pipelined. We are going to assume that they are pipelined, and we are going to show how to pipeline the execution here. And each pipeline stage operates on a different data element. So the good thing of vector instructions is that they allow deeper pipelines, because usually we are also going to have relatively long vectors. Until now, we have been talking simple examples with 4 processing elements, for example, or 6 processing elements. We will usually have more. Typically in GPUs, we talk about 32 processing elements. That's going to be the typical vector length in GPUs, as we will see. So this long vector length allows us to create deeper pipelines, because there are several advantages here. The first thing is that there are no intra-vector dependencies, so no hardware interlocking is going to be needed. We don't need to stall the pipeline because there is some dependence across the elements that are, or the operands that are being used and where the execution is happening. Why is that? Because we have a long vector and the same instruction is for every single element, right? So we assume that all these elements in the vector register are independent of each other, and the computation that happens on them is completely independent of each other. And same happens for control flow as well. There is no control flow inside a vector. Why is that? Because it's a single instruction and is the same instruction for all the vectors. Nevertheless, we'll discuss soon how we can do to enable control flow in vector processing and in SIMD processing in general. The fact that we know the stride in advance, because we have this stride register that we just presented before, is that this makes very easy to calculate the address, right? We just need a base address and then to know the stride. And now we know all, we automatically know all the addresses for all the elements that need to be accessed from memory. So there are certain advantages from vector processing. The first one is that there are no dependencies within a vector. So this makes the pipelining and parallelization work easy, and we can have deep pipelines that can have high latencies better. Each instruction generates a lot of work, a lot of operations in the end, because if we have a vector length of 50 additions, will happen at once or in a relatively short amount of cycles. The good thing of this is that with a single instruction, we just need to fetch one instruction from the instruction memory, and with that single instruction we can operate on many data elements as one, many data elements at once. And then there is no need to explicitly code loops, and as you will see, fewer branches in the instruction sequence. And also regular memory access patterns, right? Especially when we have a stride equal 1, we are going to exploit typically maximum bandwidth when accessing memory, but even if we talk about a stride larger than 1, we have a regular access pattern, and there may be ways of regular in the sense that, there is this fixed stride among consecutive accesses, And we can also exploit this regularity, maybe in order to rearrange how the data is placed. For example, imagine the matrix V that we saw before, we could transpose it. And then instead of having to access elements that are physically distant, we could access all elements of the column as if they are in the same row, right? Because we have transposed them. So we can take advantage of the fact that the accesses, the memory accesses are regular. But vector processing also has some disadvantages. And the first of these disadvantages is that it's not that easy to use them when the parallelism is, it's easy to use them when the parallelism is regular, but not so easy, not so efficient when the parallelism is irregular. We will start very quickly losing performance as we need to support irregular accesses to memory, for example, or irregular execution, control flow, and so on. And then there is another issue as well. It's that it's normally difficult to create code for SIMD processors. And that's something that Fisher pointed out in his paper in 1983, where, as you can read here, it says the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware. So here the constraint is that the hardware has certain characteristics. It's, let's say, very static in the sense that it has multiple processing elements, and we want to use them all at the same time in the best case. So we have to write the program in a smart way that can really make use of all the processing elements at the same time. And that's bring us to the, or takes us to the ways of optimizing this code and how we have to write optimized code for SIMD processors or for GPUs. We will talk about that later in this lecture. Here you have the abstract of Fisher's paper, and so I think that's very clear disadvantage that pointed out in this paper. But it's not the only one, of course. Something that we will also talk about later is Amdahl's law. Why is that? Because even though you might think that SIMD processors are great because you can operate on a whole bunch of data at once, and you can save a lot of instruction fetches and so on, the problem with SIMD processing, same as the problem with parallel processing in general, is that it has to obey the Amdahl's law. So in the end, the benefit that we can get from the SIMD processors depends on what's the fraction of parallelizable code that we have in our program. Okay, so more vector processing limitations. Memory or bandwidth can easily become a bottleneck, especially if the compute memory operation balance is not maintained, or the data is not mapped appropriately to memory banks. And this is something that happens very frequently in real world workloads, especially, I mean, both points actually, but regarding the first one, it's something very common. As you know, you guys are familiar already with processing in memory, and you know that processing in memory is motivated by the fact that accessing memory is much more costly than computing. And due to that, computing systems these days are highly memory bound in general for the majority of workloads. So imagine that now you have a, let's say, more powerful processor, because it's not just a single execution unit, a single core. Now you have an array of cores, and you need to feed all these cores, and you need to give them operands all the time, and these operands need to come from a memory that is far away, right? So that's why I mean, we will be easily bottlenecked by the access to memory. And actually, you can even put it the other way around. For example, one way of measuring, because if you go to the data sheet of your computer or your CPU, you will see what's the theoretical bandwidth that you can achieve from memory, but actually the way that we normally use benchmark, like a stream benchmark, if we want to measure what's the actual bandwidth of memory, the most normal thing is that we will use SIMD instructions, SIMD extensions, because this way we can exhaust the memory bandwidth faster. And yeah, and regarding the second point, we are also going to see some more examples later. We will understand the concept of memory bank. If the data is not placed in memory in a nice way, or put it the other way around, the execution units or the threads running on these execution units don't access the data in a nice way, we will have typically bank conflicts that will reduce the effective bandwidth that the processing elements can enjoy. Okay, let's go a little bit more in depth about vector processors. If there are any questions, you can let me know now. If not, you may want to prefer to answer later.
Yes, hi, can you hear me?
Yes, I can hear you.
Yeah, I just had a question about how these vector processors are actually implemented. Because in the example you showed in the beginning, they seemed pretty sort of specific to the one program we're trying to run. So like, I was wondering how would that, how could we generalize that? Like, what would the processing elements look like? Would it just be a bunch of ALUs with like a bunch of different like load?
Yeah, so
yeah,
so it will be something like that, as you said. It will be a bunch of ALUs probably. I mean, what I showed you before are very simplified representations, right? Are more like let's say conceptual representations of the processor, where you can see that there are different processing elements. These processing elements are actually ALUs or maybe load store units that are physically together or next to each other on the silicon. But also, as we have already seen as well, or mentioned as well, these units are pipeline, right? And if they are pipeline, what that means is that they can be operating in different cycles on different data elements and executing the same instruction on them, probably. So, so here, and as you will see, because we are going to see like, let's say, clear diagrams of real-world GPUs, where you will be able to identify the different processing elements. You will see that sometimes, I mean, actually both things happen, right? That these processing elements are replicated, so you have let's say another, or you have a multiplier, and you have multiple of them. But then, as well, each of them is pipeline, and this way you can exploit the parallelism both in space and in time. But yeah, I think we are going to see more concrete examples closer to the real world or from the real world, and you will understand that better.
Okay, perfect. Thanks.
Yeah. Okay. So
question one.
Yes.
So earlier you made distinction between a vector and an array processor, and from what you showed, it was my understanding that an array processor is the one that we would today see in for example, AVX or NVIDIA GPUs. Is that correct?
Not really, I would say. I mean, in AVX, maybe. I'm not so sure about that. But yeah, in AVX, you can assume that you have multiple processing elements next to each other, and each of the processing elements can either execute an addition or can execute a multiplication, right? So that's why you think that the array processor is closer to the AVX extensions or SIMD extensions. Yeah, however, in GPUs, so in GPUs, as you will see, I'm going to show you a picture of the layout of the GPU. You will clearly distinguish different processing elements as well. There are processing elements that are specialized for 32-bit computation. Others are for 64-bit computation. Others are load store units. Others are specializing special functions like transcendental functions and so on.
And these are, so my understanding was that a vector processor, according to this definition, is one where you have less processing elements of each type than you have elements in your vectors.
You have less processing elements of each type as you have, yeah, you could say it that way. I mean, in the let's say the pure definition that I gave you, you have a single processing element for each instruction. You have one processing element for loads, one processing element for stores, one processing element for additions, and another one for multiplications.
Okay, thanks. Yeah, I'll see if we see more examples for these. Thanks.
I think it will be much more clear when we talk about the GPUs.
Yeah, sounds good.
Thanks. And we will go back to this. Okay, yeah, vector registers. Each vector data register holds n bit values. This is something that we already know. For the data registers, we have also talked about two of the vector control registers, the vector length and the vector stride. And there is, the vector length, you know already that this defines what's going to be the length of the vector. In the end, what's this n? So how many registers we have in each vector register? And then we also have the vector mask. We are not going to talk about it right now. We will defer it for later. But in the end, the vector mask is going to be the way of implementing control flow or flow control here. The vector mask is just like a bitmap, each bit representing each of the vector lanes, each of the vector registers, and depending on what's its value, 0 or 1, the actual operation will happen or not, or the final result will be written to the destination register or not. We will see the example later. But then we can talk more about the vector functional units, and this will also help clarifying the idea as well. We said before we have a long vector. A long vector meaning we have multiple elements, and we are going to execute the same instruction on all these elements, right? And this gives us the possibility of pipeline the execution. Pipelining the execution means that in the first cycle we start executing the instruction on element 0, then in the register 0. In the next cycle, we go to the element in the register 1. In the next cycle, we go to the element in the register 2, and so on. And they start making progress through this pipeline of multiple stages, as you see. After a certain number of cycles, let's say 6 cycles here, we have the result for element 0 that we write in the corresponding register in vector register 3. Right? So this is, as I said before as well, is exploiting the parallelism in time. Now imagine that you have more of these. So what that means is that you can also execute the same instruction at the same time on another pipeline. So now we start, let's say, combining the concept of vector processor that only parallelizes in time with the concept of array processor that also parallelizes in space. But we will see a more clear example very soon as well. By the way, regarding real machines and real world computers using vector processors, probably one of the first ones and actually a very relevant and interesting example is the Cry-1 architecture. It was the fastest computer of its time. And here you have a pretty nice diagram where you can easily identify vector registers and then also like the different vector instructions for integer operands, for floating point operands as well. And also here we have scalar registers and scalar execution units as well, because even though, and recall Amdahl's law, even though this computer was super fast due to the fact of deploying these vector units. In reality, real world code also has sequential parts that cannot be parallelized. And this is why we also need to have fast scalar execution units in a complete system. You can read more about this in the original paper. And if you're even more curious, you can go on excursion to the CAV building of ETH, where you will find one of these Cray systems, actually from sometime in the 80s. And yeah, you see here a few more figures, some internal system organization, some design details, details about the functional units in terms of register usage, or what's the timing clock periods to complete an instruction, and so on, and a few more system configurations of configuration options. And this is Seymour Cray, the founder of Cray. He has this well-known quote where he said, if you were plowing a field, which would you rather use, 2 strong oxen or 1024 chickens? So that will depend on the computation that you need to do, as I said before. If you have some workload that is inherently sequential or only modestly parallel, you will probably choose the 2 strong oxen. However, if your parallelism is data level parallelism, and it can be massively parallel execution, you probably prefer the 1024 chickens. But then another thing that we have to talk about is how to access data from memory to feed these vector processors or array processors. And to do so, we need to have banked or interleaved memory. And actually the Cray one already had it with 16 memory banks. Let's talk about how to load and store vectors from and to memory. In the end, because we are operating on vectors, we need to load or store multiple elements. And these elements, as you know already, they are separated from each other by a constant distance. This distance is the stride. For now, we are going to assume stride equal 1 because it's going to be easier to understand everything. And we are going to discuss how to access memory. Elements can be loaded in consecutive cycles if we can start the load of 1 element per cycle. And this way, we can sustain, hopefully, the throughput of 1 element per cycle. But now the question is, how do we design a memory that allows us to access 1 element every cycle if normally the latency of access to memory is longer than a cycle? And that's the answer for that is banking the memory or interleaving. So banking the memory and interleaving the elements across the banks. Here we have a simplified representation of what would be a banked or interleaved memory. Notice that here we have 16 memory banks, and each memory bank has its own MDR, where we are going to to either place the data element that we want to write to bank 0, or where we are going to store temporarily the element that we read from bank 0, and the MIR is where we put the address that we want to access. And as you see, these are connected to the data bus and the address bus, and from there to the CPU. So the memory is divided into banks that can be accessed independently, and they can be accessed independently because each of them has their own data register and address register. And as you are going to see, we can start and complete 1 bank access per cycle. So in the end, we can sustain as many concurrent accesses as we have banks, right? So what's going to be the idea here, essentially? The idea is that whenever the CPU requests a whole vector, let's assume that the vector length in this case is 16, so we need to read 16 elements from memory. We are going to interleave these elements on the memory banks. So element A0 is in bank 0, element A1 is in bank 1, and so on. In the first cycle, we write here in the MAR the address of element A0 that resides here, and we start the access that takes a certain amount of latency, certain number of cycles to complete, let's say 11. And after 11 cycles, we will have the value that we wanted to read here in the NDR. But now notice that right after starting the access to bank 0, 1 cycle later, we can start the access to bank 1. And 1 cycle later, we can start the access to bank 2, and so on until bank 15. And what that means is that after 11 cycles, remember that I said that accessing 1 element in bank 0 takes 11 cycles. After 11 cycles, we have the value that we wanted to read here in the MDR. And 1 cycle later, we have it here. And 1 cycle later, we have it here, and so on. So this way, we are essentially reading one element per cycle, even though the latency of access to memory is much longer than one cycle. It was 11 in the example that I just gave. Yeah, how are the addresses calculated? We said before, one of the advantages is that calculating the addresses that we need to access from memory is very easy. Why is that? Because we just need the base and the stride. And what we have to do when generating the addresses to access data in bank 0, bank 1, bank 2, and so on, the only thing that we have to access to do is using another to calculate this. This can be, let's say, our load store unit has this other gets the base address of array A, gets the stride, and cycle after cycle adds the stride to the base or to the value that we have, the address value that we have here in this accumulator. And so right, and then we send it to the MIR of the different banks and start accessing the banks. So yeah, that's essentially what we are doing here. In this case, by the way, we are considering stride 1, as I said before, is the simplest case. We assume here that stride is equal 1, that consecutive elements are interleaved across banks. And also another important thing is that the number of banks is greater than the bank latency. And if this happens, we will be able to sustain one element cycle throughput. This condition here is also important because if you want to get one element every cycle when the memory starts outputting the elements, you need to have more banks than the latency, right? Because this way, before you finish to send addresses to the different banks, you're already receiving data from the initial banks. Okay, we are going to keep analyzing and discussing all these concepts now with a more complete example. Remember this code from before, where we have a for loop that goes from 0 to 49, 50 iterations, where we read one element from A, one element from B, we add them, divide by 2, store in Z. Now we know that we can write this in we can write a vector program with this, or a SIMD program to replace this sequential program here, and we are going to see how. The first thing is to analyze the scalar code that is let's say the assembly code that we would run on a sequential machine. Notice that first thing is to load 50 into some register that we are going to decrement cycle after cycle until we have gone through the whole array. Then we have 3 registers to store the addresses of A, B, and C. And now you can see here the body of the loop. First of all, loading from whatever memory position that stores the element of A, loading the element of B, we add them here. Now we shift right, because dividing by 2 is essentially shifting 1 bit to the right, as you know, and then we store. Finally, we have to decrement the counter. In this case is, or the index, in this case is R0. We decrement the counter and compare to 0. If it's not 0, then we jump to X and continue the execution. We start with element A0 and B0, then element A1, B1, and so on. So if you count what's the number of instructions here, you can count them 1, 2, 3, 4, and so on. But then when it comes to executing these instructions on the processor, it will take longer, right? It will take a certain number of dynamic instructions, which are the actual instructions that are executed. If you count them for this particular example, you will see that in total there are 304 dynamic instructions. Yeah, now the point is scalar execution time on an in-order processor with one bank, we can estimate it, right? The first 2 loads in the loop cannot be pipelined. So this means that it's 2 times 11 cycles. We continue with the example that I gave you before, latency of access to the memory. I said 11 cycles. That's exactly what we have here. And you see also in this column for every single instruction, what's the number of cycles that needs to be executed. Remember that this is the execution of this code, this scalar code is going to happen on a sequential machine. And what that means is that before starting this load instruction, we need to finish the previous load instruction. And before starting this add instruction, we need to finish the previous load instruction, right? So that's the simplest case. That's the case where we only have a single bank. So if we have a single bank in memory, we cannot parallelize the accesses to data in memory. So in that case, we need 22 cycles to obtain the 2 operands for the first addition, right? How can we make this more efficient? How can we accelerate this? Well, instead of having a single bank, let's have more than one bank. We can also use banked memories, and we actually do it, banked memories for sequential processors as well, because this way we can hide the latency of the access to memory, right? And we can obtain much more throughput from memory. So assuming that we have, let's say, 16 banks for the previous example, the 2 loads can be pipelined, and one cycle we issue the load for element A from bank 0, the element of A from bank 0, in the next cycle, the element of A from bank 1, and so on. And we can do the same for the elements of B as well. So this way, our access to memory will be much more productive, and this way we can reduce the total number of execution cycles. By the way, going back to what should be the number of banks, remember that I said before, the number of banks ideally will be higher than the latency in cycles of the memory access latency, right? And here you have a little bit more of this explanation, because we are assuming an example where the access, the memory access latency is 11. We need 16 banks, which is greater than 11, to ensure that there are always enough banks to overlap enough memory operations to cover the memory latency. Okay, now we are going to continue with the same loop, with the same example, but now we are going to treat it as vector code. This is our sequential code, but if we write the vector program for this one, you will see that, now the code clearly is much shorter. As you can see, let's assume for now that the vector length can be 50, which is actually the number of iterations in our sequential code. The vector stride is equal 1 because we are accessing consecutive elements in arrays A, B, and C. And so we only need to load these 2 values to the corresponding register, and then we can start executing, let's say, productive instructions. The accesses to memory, the addition, the shift register, and the store operation. And because this is a vector machine or a vector or SIMD processor, we just need to write 1 instruction for all 15 elements, right? So this is the vector load that loads in V0 the 50 elements coming from A. This second vector load loads in V1 the 50 elements coming from array B. And then we execute this vector addition, vector shift register, and vector store. And now if we think about the latency of each of these operations, except the first 2 that are simpler operations that where we just write a single value onto a single register, so they take only 1 cycle. The rest of them can be pipelined in some way, and that means that we can make them more efficient and more productive, and we will get higher throughput. Remember that in the case of accessing memory, for example, for this vector load, we will have to pay for sure the latency of a single access that is 11 cycles, but after those 11 cycles, we will start getting 1 element from memory every cycle, right? And how many elements in total we are going to get? Vector length, V length. So that's why the total latency of this vector load instruction is 11 cycles, corresponding to the first element. When we send the first address to bank 0, we have to wait 11 cycles until we get the value. And then after that, because we have been issuing requests to all the different banks, we will get 1 more element every cycle coming from a different bank. So that's what gives us these latencies for a vector load of A and vector load of B. And for the addition, shift register, and store operations is essentially the same. The only thing that changes is what's the latency of the first element, of the first operand. In this particular example, additions take 4 cycles, shift registers, shift right operation takes 1 cycle. So if you count what's the number of dynamic instructions here, you see it's much lower than what we have seen before. It was like 300 dynamic instructions. Here is only 7 dynamic instructions. Okay, now we are going to see how this code executes on an actual machine. We are going to start with a simpler case. Let's assume that there is no chaining. Chaining means that you can send a value read from memory right after it arrived. You don't have to wait for the other elements of the vector to arrive. But for now, we are going to assume no chaining. There is only one memory port, but the memory is banked, is interleaved. It has 16 banks. And if we execute our code using the latencies that we have seen in the previous slide, and assuming that the vector length is equal 1, we will see that it looks something like this. First of all, 2 cycles to load the vector length and the vector stride. Then we pay 11 cycles for the access to element A0, then 49 cycles, which is vector length minus 1, then the access to array B, then we perform the additions, shift right, and store. And as you see, all these operations happen sequentially, one after the other, because we are starting from the assumption that we need all the elements in a vector register before starting the execution of the next instruction. And this takes 285 cycles. That is already much faster than the execution of a scalar processor that we saw before. But now we are going to keep discussing ways of optimizing this execution. And here is where we start using vector chaining. That essentially means data forwarding from one functional unit to another functional unit, something like this. You access memory from using the load unit and write some data in the vector register. Remember that this is a pipeline access to the multi-bank memory. We start accessing bank 0, then bank 1, then bank 2, and so on. So after a certain number of cycles, 11 in our example, we get the first element, A0. So in the previous slide, we were assuming that before doing anything with A0, we have to wait for all the other elements of A to arrive to this vector register 1. But now we are going to use vector chaining that essentially consists that right after receiving one value, let's say A0, we can send it to the next execution unit, that in this case is a multiplier, right? And we are also fetching the corresponding element from B0 and performing the multiplication and writing in B3. And we can extend this even more, right? We can have more units, in this case another, and continue doing the chaining. So what that means for our timeline is that after having loaded all elements, all elements from A and having loaded the first element from B0, we have 2 operands at least to start the execution of the addition. And right here, right at this point, we already have A0, we have B0, and that's why we can start executing the addition for these 2 elements during these 2 cycles. And after that, we will complete one by one the execution for the remaining elements of from A and B, and then shift right, and then the store operation. So as you see here, we are creating this chain that gives us way more performance than the previous execution. In total, actually 182 cycles. But we can optimize this code even more. Right now, we are on the strict assumption that 2 loads cannot happen in parallel. And this is because we are assuming that we have a single port, a single unit that calculates the addresses for accessing bank 0, bank 1, and so on. And what that means is that we either use it for this vector load or use it for this vector load. And what that causes as a result is that we have to wait until all accesses to array A from this first vector load are complete and until we can start with the execution of the next vector load. But now we are going to assume, for example, that we have 2 load ports and 1 store port. So what that means now is that we won't have a vector load delayed or a vector store delayed because another memory access is being executed. So right after starting the execution of the first vector load, because we have 2 load ports, we can also start calculating instructions for the second vector load, and this way be much more efficient. And this way we will also have the first 2 operands, A0 and B0, in the corresponding register of the vector registers much earlier, and we can start the execution of the addition and later operations or instructions much earlier. So in total, now you can compare it 79 cycles, so it's like 19 times faster than the original implementation. So now one question here is, what if the number of data elements is greater than the number of elements in a vector register? So for example, imagine that we have 527 data elements, but the size of our vector registers is only enough for 64 elements, right? We only have 64 registers in each vector register. So that's the case, and actually that's, as you will see, what happens in GPUs and in real SIMD processors, is that this maximum vector length is limited. And when this happens, what we simply do is executing the instructions in multiple iterations, right? For example, in case of vector length equal 64, that we will need 8 iterations. If vector length is equal 15. Oh, wait, here, what's the problem? I think there must be something wrong here, because it must be more than 1 iteration when vector length is 15. But anyway, I will. No, sorry, I was misunderstanding this. So it's exactly the way as I was explaining. I have 527 data elements, and I have to distribute these 527 data elements across iterations using the vector registers that I have available. And my vector registers and my vector length have a maximum of 64. So what that means is that I should take these 527 elements and operate on them 64 after 64. So it's first the first 64, then the next 64, and so on. And I will have 8 complete iterations of 64 elements. But after that, I will have kind of a tail, and this tail also needs to be computed, right? In this case, I will have a final last iteration that is incomplete. Incomplete in the sense that it doesn't need to use the 64 elements in the vector registers. It just need to use 15 of these elements, and that's why we will need to change in software the value of the vector length. Remember that we move the actual vector length that we want to this vector length register that we presented before, and this is what is called the vector strip mining. This idea of getting rid of those parts of the material that you don't know, that in this case would be the lanes or the vector registers that we are not using, right? We reduce the vector length from 64 to 15, and the rest of it, we simply don't use it. Okay, one more question. What if a vector data is not stored in a structured fashion in memory? What if we have irregular memory accesses to a vector? So the idea here is to use indirection to combine and pack elements into vector registers, and we perform what we call scatter and gather operations. Doing so also helps with avoiding useless computation on sparse vectors. And here you can see one example. Observe that we have a simple loop similar to the one we had in the previous example, but now the difference is that the access to array C is an indirect access. So before accessing array C, we have to go to array D, we read the value in array D, and then that's the address, that's the position of the element, the corresponding element of array C that we want to use in each iteration. We can write the vector code for this. As you see, first of all, we load the vector load the indices from the D vector, and then we have to do this load indirect where we calculate the address to access using this base register for array C and the vector register that contains the indices from array D. And this is called a gather operation because we are gathering elements from memory and we are storing them in our vector registers. Actually, they will be stored in this vector C that we later use for the addition. And same thing we can do when we write to memory, right? In this case, instead of calling it gather, we call it scatter, but in the end, it's the same idea as well. We are doing indirect accesses. Notice that this is the way we access sparse matrices, for example, when they are in memory, right? So here you have in this example, you have the index vector. These are the positions where we have to store the elements that are in principle in the same, in consecutive registers in the same vector register, and in the scatter operation, we write this element in the position given by this index element of the index vector, this element in this position, this element in this position, and so on. And after the scatter operation finishes, the memory will look something like this. So now we know how to, let's say, operate using vector and SIMD processors in the regular manner when the computation is completely regular. But now we also know how to optimize the access to memory using banked memories. We know how to deal with, let's say, incomplete vectors when we don't need to use all the lanes, all the registers in a vector register. We can change the vector length. And we also know how to access memory when we have irregular accesses, right? It was simpler when we had regular accesses with stride 1 or where the stride was fixed. But even if that's not the case, even we have more complex access patterns that require indirect indexing, for example, there are also ways of doing it with gather and scatter operations. Now, the next thing, in order to support, let's say, this irregularity that we are trying to support now in SIMD processors is to deal with conditional operations. Imagine that we modify or
I think we have a question here.
Yes. Okay, great.
How does the gather and scatter affect latency? Because potentially, like the indices could be to the same bank, and then you wouldn't have like one data element per cycle.
Yeah, that's actually a very good question. That will depend on your access pattern, of course. When it comes to accessing, so in the gather operation, for example, we talk about array D that contain this array D contains the indices. That's easy, right? Because all these indices for the whole vector are in consecutive memory locations, as you see. But now the problem comes when executing this load indirect, right? You are going to obtain some let's say some final addresses that you want to access. You obtain them from adding the base containing in RC with the corresponding register from VD. You get these addresses, and now you have to send these addresses to memory, right? And as you said, some of them may fall in the same bank. So what's going to happen is that, of course, you will have bank conflicts, and this will delay the arrival of the data from memory. That's what's going to happen. We are going to talk about the bank conflict soon, but we will focus on strided accesses that are probably easier to understand because they don't involve any array of addresses as array D here. But yeah, you will see that it's essentially the same thing. Of course, the best, let's say, most efficient way of accessing memory is when we don't have bank conflicts, when we can operate on all banks at the same time and exploit all the parallelism that the banked memory provides. Yeah, but as I said, we are going to see the example in like 3 or 4 slides. Okay, yeah, anything else?
Yeah, I had a follow-up question that's somewhat similar. I was just wondering, back when you first started talking about the sort of bank, you're kind of assuming the whole time that your vector will be evenly distributed throughout. Is that always the case? That's yeah.
That's also a very good question. I mean, what would you do? I guess that would be the first approach, right? Let's store one element, because we will normally have. I'm not saying that that's. I mean, it's actually I would say in all programs, even though they have very regular memory accesses, you will have streaming access patterns, what means that you access consecutive elements in memory, right? And from that point of view, I think it's reasonable to store consecutive elements in consecutive banks, because it will be very frequent in real world programs to have a stride equal 1. But that also connects us, or what your question also connects us to the way, or one of the ways that we can come up with in order to deal with bank conflicts and reduce them. If you know in advance that the accesses are strided or irregular in some way that you can predict, or you can know in advance, you would be able to reshape the way that data are stored in memory in order to reduce the number of bank conflicts.
Okay, yeah. So I guess that the memory controllers in vector processors are much different than they would be in regular sequential processors.
No, not at all. I'm saying you as a programmer.
Oh, okay.
Of course,
we have control.
Of course, we can also discuss. Well, no, I mean, we can also discuss hardware support. And actually, if you look at current GPUs, for example, and you think about the way current GPUs access memory or map the data onto memory, you will see that it's not as simple. I mean, in some of the memories that are banked is like that, and that's the easiest or the simplest case. But when it comes to accessing the DRAM memory, and you know that DRAM is also a banked memory as well, it's more complex than that. Normally these days, they are using hash functions in order to calculate what's the physical destination. And that's also one of the potential solutions that I'm going to mention in 3 or 4 slides.
Okay, yeah, I guess I can wait 3 or 4 slides then.
Yes.
Thank you.
We will talk about that more, don't worry. Okay, so yeah, we are discussing how to access memory, now how to execute, let's say, more irregular computation, right? Like in this case, where we have flow control, we have this if statement here. We first check what's the value of A. If it's not 0, then we perform the multiplication, because otherwise performing the multiplication by a 0 value doesn't make any sense. So that's why we are checking this in order to save energy, for example. And the way that we execute this is by using mask operations. And the mask operations require to use the vector mask or the V mask register. Yeah, so in order to implement this simple code with a vector or SIMD code, we would first load the elements from A, we'll load the elements from B, and now notice that we have to compute the bits, the mask or the bit mask that will be stored in this B mask register. And to do so, what we do is comparing the elements contained in V0 to elements to value 0. If they are either 0 or 1, will be written in this bit mask. And then depending on the bit that we have in the bit mask for the corresponding lane or for the corresponding register, we will execute this multiplication or not. Or we may execute the multiplication, but finally not store the result in the corresponding output position. That will depend. There are different ways of doing this, as we are going to see. So this is what we call the predicated execution. I think that you must have already heard about predicated execution, and we call it this way because in the end the execution is predicated on the mask bit. Here you can see another example with masking. In this case, it's a little bit more complex because we have an if-else statement. So we first obtain the mask, same as before, performing one comparison and loading the corresponding bit in the corresponding position of the VMask register. After executing the first operation here, that is storing the element of A in the corresponding position of C, we complement the mask because this is an else statement, and for the remaining lanes, we will store an element of B in an element of C. And now, how are these mask vector instructions executed? The simplest thing is what is called here the simple implementation. It simply computes as if all registers were active, all lanes were active, and only at the very end, when it comes to writing to the output register, in this case register 0, it will disable the write enable signal, right? And this way we don't write to the corresponding register, and that's all. That's how the predicated execution is implemented. Something smarter, let's say, would be to check the vector mask in advance, and by doing so we could even save execution cycles, because we would never start the computation, the multiplication, for example, for the operands that are 0, or for the operands that have the corresponding bit in the mask equals 0, right? And this is what is called the density time implementation. Which one is better in terms of performance? We may expect that this one will be better because it's saving more cycles. In terms of complexity of the implementation, this one will be simpler as well. And because the hardware is going to be simpler, it might be also be able to run at a faster frequency. So in the end, it's not that easy to decide which of the two options to choose. Okay, now let's talk about bank conflict. Some issues with the stride and banking. You guys were asking before, how is the memory mapping, right? How are the data stored into the different banks that we have? We can do it in different ways. We can use a row major layout, we can use a column major layout, but in the end, it's another thing we have to take into account is how are the elements themselves mapped onto the different different banks. Let's go back to the example of the multiplication of matrix A and matrix B. We want to compute this A times B equals C. So first thing, as you know, is loading the elements from array A, then loading the elements from array B, and notice that there are different strides here, and different strides may cause bank conflicts. So in the case of a stride equal 10, I think it's quite clear if you think about a memory with 16 banks, for example. 10 and 16 are not prime relatives, and what that means is that you will end up having some elements falling into some elements of these columns falling into the same bank, and when it comes to accessing them, we will have to wait, for example, for say reading element 30 until element 10 has been accessed, right? So that's essentially a bank conflict, but that's something that we I mean, in principle, cannot avoid if we go just with the most straightforward mapping, and we can think about ways of solving these bank conflicts. One way is, for sure, including more banks or using more ports per bank, because also, you know, each bank may be able to sustain one access or two accesses or maybe more accesses at a time. Of course, all these solutions imply a hardware cost, because you need to make your hardware more complex or at least larger. But then there are also like possibilities like trying to find a better layout depending on what are the characteristics of our workload. If we go back to this example, I think a very straightforward way of improving the layout for array B is transposing it, right? And now all columns can be accessed as if they were rows, and this way we have sequential accesses to consecutive bank, or consecutive accesses to consecutive banks. But this may not always be possible, right? And for example, when we have indirect accesses, random accesses, if we don't have knowledge about how these accesses are going to happen, it's much more difficult. But in that case, we can try, let's say, closer to the hardware techniques to do better mapping. And here is where it comes, the randomized mapping that I mentioned before, that NVIDIA GPUs already use. Like you use a kind of hash function that gives you what's the destination address, and this way you minimize, as many papers have proven, including this seminal one from Bob Rao. These are ways of randomizing the access to memory, and this way reducing the amount of bank conflicts for at least certain access patterns. And now one question might be, are they, universally efficient? Yeah, of course not. Regardless of what's the randomized mapping that you use, the hash function that you're using, there might be ways of causing bank conflicts as well. So probably there is no universal solution to solve bank conflicts. And here you have the abstract of the paper from Bob Rao. Is it, let's say, different solutions, are they more or less clear? Do you want me to clarify anything? Okay, I guess it's fine. Anyway, we are going to talk probably about bank conflicts later as well when we talk about the GPUs. Okay, so as you see, array and vector processors are a kind of very similar thing. It's more like a theoretical distinction, but in reality, modern processors are a combination of both. Typically, GPUs, as I said before, they are going to combine data parallelism in both time and space. So in the end, they are going to do kind of these two things at the same time. And you can actually see like a first example of this here in this slide. Imagine that we need to execute this vector add, and we have a single unit, right? If we have a single execution unit, we exploit the data parallelism in time, in the pipeline. However, we may have more than one of these instructions units. We may have 4, right? And if we have 4, we can distribute the different elements of the vector registers across the different units that we have in a space. And by the way, all these units might be the same one, capable of executing different instructions, or maybe are specialized and they can only execute one instruction. That's irrelevant here. But as you see, the execution itself of the 28 elements that this vector has are both in time and in space, and this matches better the current shape of SIMD processors and also GPUs. And then regarding how the vector registers are accessed by the functional units, by these ALUs or pipeline ALUs, each of them have their own vector registers, right? So in the end, we have a whole register file, and every time that we execute a program, and depending on what's going to be our vector length, and depending on what are the register needs of each of the threads or lanes executing here, we will have to assign more or less registers to each of the individual units. But yeah, in the end, it's kind of a statically partitioned register file with the vector registers assigned to the different functional units. And when I talk about lane, I've said lane several times already without defining it. When I talk about lane, I talk about all of these. You see, I talk about functional units, and I also talk about the registers that contain the operands for the specific functional units. So in this particular example, as you see, we have 4 lanes, right? Okay, so yeah, I think more or less we start having like a I hope you have now a more clear view of vector processors, array processors, how they can be combined. In this particular example, you have a program that executes load, multiply, and add instructions. Every single cycle, we issue a new instruction, as you see. But now it turns out that the vector length that the programmer defines in this particular example is 32, but we only have 8 lanes, meaning that we only have 8 processing elements, meaning that we have to, or we need 4 cycles to start the execution for the 32 elements of the vector, right? And after we are done with the 32 elements, we can go to the next load instruction or the next multiply instruction or the next add instruction. And as you see here, at the same time, we are executing different instructions on different units. In the same space, we are executing the same instruction on different values as well. So this is the combination of both. Okay, now one of the things that we said before is that one of the disadvantages of SIMD processors is that it's difficult to write the code. Luckily, compilers have improved over the years and they are even able to extract parallelism from the code. In a code like this, where in a typical scalar sequential execution, we would do something like this, iteration after iteration, we load, add and store, load, add and store. We can have a smart compiler that realizes that many of these instructions are independent and they could be executed in parallel. For example, this load here and this load here are accessing 2 different elements of the same array, but the access to them could happen in parallel, right? And same for these 2 loads, same for these 2 adds, same for these 2 store. A compiler can be smart enough to be able to identify or find where are dependencies or where there are not dependencies and generate the vectorized code, and this will save a lot of effort to the programmer as well. Okay, we are going to start summarizing about vector processors, and then we are going to do a short break, let's say 10 minutes. I think it will be fine. Vector and SIMD machines are good at exploiting regular data level parallelism. As you know, same operation performed on many data elements. This improves performance, simplifies the design, and we can achieve very good performance improvement, but also the amount of improvement, the amount of speed up that we can achieve thanks to a SIMD processor is going to be limited by the actual vectorizability of the code, or in the end, by the actual amount of data level parallelism that we can exploit. Remember Andal's law, and remember that in the end, even the fastest vector machine of its time, that was the Cray 1 processor, it also was the fastest scalar machine, because their designers knew that vector execution or SIMD execution was not enough to do well and high performance for many important workloads containing also serial fractions of the execution time. And yeah, we can mention some of the existing ISA SIMD extensions. In Intel, we have MMX, SSE, AVX. I think the most recent ones are AVX 512, if I'm not wrong. But we also see these extensions in other processors like Power, IBM Power, ARM, AMD, even in RISC-V processors, there are SIMD extensions. And this is the slide about Andal's law that we have already discussed before. Now, I think we can do a break until 45, until what time? Okay, until 3 p.m. Let's do a break, and yeah, and after that we will talk briefly about SIMD operations in modern ISAs, and we will continue with GPUs. Okay, I think we are ready. I hope we are ready to continue. So as I said before, now we are going to discuss, well, I don't know if there are any questions, burning questions at this time. If not, I will start. Okay, as I was saying, we are going to present as well like what are SIMD operations in modern ISAs, or I'm going to give you one example, which are the MMX instructions that were incorporated to Pentium processors x86 architecture back in the 90s. So the idea of SIMD, as you know, is having a single instruction operating on multiple pieces of data at once. And there are some applications that can benefit a lot of this, like graphics and multimedia applications. And actually, these were the main motivations for SIMD extensions when they were proposed for the first one. Also, for some of these some of these applications, we may not require like whole precision, like 64-bit or 32-bit precision. So in the end, the idea here can be dividing the current ALUs that we have in a system in a way that they can operate on smaller data types. For example, if you have a 32-bit multiplier, if you don't connect the carry from the 8 lower, less significant bits to the next significant bits, if you don't connect the carry, you will have 4 additions at once in the same amount of time that you had one addition for 32-bit elements. And that's the key idea in the Pentium MMX operations. It's kind of a array processing, but it's more limited, as you can see. But it can operate on different data types. For example, 8-bit bytes, or 4 16-bit words, or 2 32-bit double words, or 1 64-bit quad word. The limitation here is that the stride should always be equal to 1, and that's why we cannot consider this like a complete array or vector processor, but kind of a simplified way of doing SIMD processing in current CPUs. And if you want an example here, you can see kind of a simple example where we want to do the overlay of a human in the image X on top of the background in image Y. So this is image X, this is image Y, and as you see, the image X has the figure of one woman, and behind we have a blue background. So the idea here is to generate a new image where the blue background is replaced by the blossom background of image Y. So things that we need to do is, first of all, compare all the pixels of the input image X and check whether they are blue or not. And if they are blue, we will, and depending on that, we are going to generate a bit mask that we are going to use to for the later execution. So if the corresponding pixel is blue, the corresponding bits in the bit mask are all going to be equal to 1. If the pixel is not blue, that is, it belongs to the woman, then the corresponding bits in the bit mask will be 0. And by using this bit mask, we can easily compute the output image with the woman in front of the blossom. This is our blossom image, and notice that here we are using the mask as such. So wherever we have, as is, so wherever we have 1, 1, 1, we will have the corresponding pixels of the blossom image in the output register. So here the operation that we are executing is an AND operation. So by ANDing these zeros and these Y7, we obtain 0. By ANDing these ones with this Y5, we will obtain this Y5. And it's exactly the same, but the other way around for the image itself. In this case, what we do is computing and not operation. So we do the AND operation and then we invert the output. So in some of the cases we have blue pixels. In some other pixels, they are not blue pixels, so they correspond to the woman. We apply the mask in this case, and then we obtain these intermediate results that now we combine with the intermediate results for the blossom image, and finally we obtain the final image that has the pixels from the woman, from the original image of the woman, and pixels from the blossom, and that's going to be the result, as you see. And here you can see the code, and you can find many more details and also more examples in the original paper, which is one of the papers that I recommended in the beginning of the lecture. Okay, more SIMD operations in current machines. We can find them in modern machine learning accelerators. One good example is this Cerebrus wafer scale engine that you have probably seen before in this course. It's kind of a wafer size processor composed of multiple tiles, and as you can see, way larger than the largest GPU of its time. This is the version from 2019. This is the newest version from this year, 2021, that is essentially twice as fast as the previous version, but still keeps being much larger in terms of die size, and also in terms of number of transistors and peak computational power than the largest GPU. Now, the difficulty with such a huge engine is to how to map the computation, right? And there are even challenges to contests to deal with how to map different applications. In particular, the applications these guys are interested in are machine learning applications. You know, for example, neural networks composed by multiple layers, like convolutional layers, pooling layers, fully connected layers, etc. And because we have on the die so many compute elements, what we have to do is distributing the computation in some way. So as you can already see here, we will have different processors on the same die, different processors operating, performing different operations, right? Because in the end, these different regions of the wafer are working on different layers of the neural network. But at the same time, and as we are actually going to see in a couple of slides, internally, each of these are SIMD engines, and this takes back to the Flynn's taxonomy of computer, where we remember have SIMD and also MIMD processor. So in the end, this Cerebrus wafer scale engine is kind of a MIMD machine that is composed by SIMD processors. And we take a look at this is the whole wafer scale engine. As you see, it's composed by multiple single dies or multiple of these tiles, more than 4,000 tiles, and then each of these tiles is essentially a SIMD processor. If you take a closer look here, you will see that we have four-way SIMD fuse, multiply, accumulate FMAC units. These are key operation for machine learning workloads these days. There are also some address registers to access the corresponding data from a local memory that is an SRAM-based memory. And this SIMD processor, it's pretty efficient because it essentially can read two operands in one cycle, and it can operate, not two operand, actually it can read, let's say, four values for each of the operands, if it's A and X in one cycle, and feed the corresponding SIMD FMAC units to perform the fuse, multiply, accumulate operation. So this is an example of SIMD machine, or SIMD processor in a real machine. We are going to we are going to start in a couple of minutes with another representative, probably the most representative SIMD processor these days, that are GPUs. But before that, I want to very briefly also give you a refresher on fine-grained multithreading. And why is that? Because as you're going to see next, GPUs are not only SIMD processors, but they are also fine-grained multi-thread processors. The idea in fine-grained multi-threading is to have multiple hardware contexts, meaning a hardware thread context, meaning the program counter that you need for the specific core to know what's the next instruction to execute. And you also have registers. You have also multiple registers that are divided into parts assigned to the different thread contexts, right? And essentially the idea in fine-grained multi-threading is to switch to another thread of execution every time that we cannot have two instructions from the same thread on the pipeline. Why? Because they are dependent. For example, you may have an access to the main memory that usually takes very long, like hundreds of cycles. And so the next instructions from the same thread are dependent on this access to memory. So we have to wait, right? And while we are waiting, we can start scheduling instructions from other threads, and this way make good use of the pipeline. And you can see kind of a pipeline here where you can easily identify the different general purpose registers, different color means, different thread, and also the different program counters as well. So whenever, let's say, the yellow thread has to gets stalled because there is a long latency operation, like for example, an access to the main memory, the fetch unit or the thread select unit here that we have, we can start fetching instructions from different threads, and this way hide the pipeline, hide the access, the long latency access to the main memory. So there are advantages here. No need for dependence checking between instructions, because one there may be likely only one instruction in the pipeline for a single thread, and if there is more than one instruction from the same thread, it's because these instructions are independent, and there is a way of knowing that. Maybe the compiler can help on that. Maybe some hardware units can help on detecting what are the instructions that are independent of each other. There's no need for branch prediction logic, and we can use what would normally be bubbles in a conventional pipeline, in order pipeline, for example, same as the ones that you may have studied in basic computer architecture courses. But now we can use the bubbles to issue and execute instructions from different threads. So that in the end improves the system throughput, the latency tolerance, utilization. Disadvantages is that the hardware is more complex, of course. You need more resources like PC, register file, thread selection logic, etc. And in principle as well, single thread performance might be lower than in a system that doesn't implement fine-grained multi-threading, and also there might be resource contention. Why is that? Because in the end we have shared resources here, shared across different threads, and they are going to compete to access caches, to access memory, and so on. And then we still need some dependency checking logic between threads, because, for example, when it comes to accessing memory, we cannot issue a store after the corresponding loads, if they are dependent, are complete. But anyway, if you want to recap and refresh more about fine-grained multi-threading, please take a look at this lecture from Professor Mutlu, and here you have links to more lectures as well. And now it's time to start with graphic processing units, GPUs, and as you will see, and as I have already mentioned before, GPUs are SIMD engines underneath. What that means is that the instruction pipeline operates like a SIMD pipeline, like, for example, an array processor, but it's not even an array processor. As I said before, it's a combination of array and vector processor. As you will see, the key difference with respect to SIMD units, so SIMD engines or SIMD processors, it's not only that GPUs use fine-grained multi-threading, as we will see, but also the way that we program them. We are not going to use vector or SIMD instructions here anymore. We are going to program in a much easier way that is using threads. So we are going to quickly, you will quickly understand this. But first of all, we have to distinguish between what we call the programming model, that is a term that refers to software, and the execution model, that is a term that refers to hardware. Programming model refers to how the programmer expresses the code, and it can be different ways. You, as a programmer, can write a sequential C program, You can write a parallel program, for example, if you use AVX instructions for, let's say, SIMD execution. You can write the data flow multi-threaded. If you use pthreads or OpenMP, you would be writing parallel code, right? But then the execution model refers to how the hardware executes this code. And what this means is that you have different types of hardware. And in the end, there is a connection between the programming model and the execution model, but they are different. They can be very different as well. So for example, you may write a sequential program and execute it on an out of order processor, right? And the out of order processor, as you know, will be able to extract instruction level parallelism, which means that it will be able to execute instructions in parallel, even though you wrote a completely sequential code. Or you can also have an SPMD model, single program multiple data model, which is, as you will see, very similar to the multiple instruction, multiple data model. You can execute a code written in the SPMD model on a SIMD processor. And this is what GPUs do. But you know, in order to understand much better what's the distinction among programming model and execution model and the different types of programming model or execution models that we may have, let's go back to our simple code, this for loop that we already know how to execute on a scalar machine, and we also know how to execute it on a SIMD machine as well. Remember that in the scalar machine, we will go iteration after iteration, first iteration 1, then iteration 2, and so on. And then we can have a processor that extracts instruction level parallelism in some way. If it's completely sequential, then probably there is not much to do. But we could also write this code in a data parallel manner, or we could write it in a multi-threaded manner. So let's take a look at the first case. The programming model 1 is sequential or SISD. This is SISD. I write it in C. It's for a single thread, but I can execute it on a pipeline processor. And if it's on a pipeline processor, that means that I can launch onto the pipeline instructions that are not dependent of each other. For example, these two loads are independent of each other. So I can start the execution of them. So I can start the execution of the second load one cycle after the first load. So that's a way of obtaining instruction level parallelism. Or I can use an out of order processor, and this way extract even more instruction level parallelism, because the processor could realize that these different iterations, iteration 1, iteration 2, are independent of each other, and schedule the execution of instructions on the available functional units. Or I can have a superscalar or a very long instruction word processor. In a superscalar processor, I have multiple execution units that I can use at once. In a vector, in a VLIW processor, I can have the compiler extracting what's the available instruction level parallelism and creating these long instructions and executing them in the same cycle, let's say. Right. The second programming model is, now we write parallel code, we write SIMD code, and the realization here is to observe that each iteration is independent of each other. That this is something that we saw before in the SIMD part of the lecture. We have already seen that because these two loads are independent, I can write a single instruction for both, right? A vector load, or for these two, a vector load, for these two, a vector add, for these two, a vector store. So now the programmer or the compiler generates a SIMD instruction to execute the same instruction from all iterations across different data. And this normally will be best executed on a SIMD processor, right? By the way, this could also be executed on a SISD processor as well. The only thing that the SISD processor will have to do is replacing each of these vector instructions by a function that goes over all the elements of the vector, right, in a sequential manner. So in the end, programming model is different from execution model, as you see. Another way of writing this program is in a multi-threaded manner. It's a different programming model as well. So here, for each different iteration, I'm going to create a different thread of execution. This iteration 1 is assigned to thread 1 or thread 0. This iteration 2 is assigned to thread 1, and so on. And this could be executed on a MIMD machine, right? If I have 100 threads, I can execute this 100 thread on the available cores of my multi-core processor or my multi-core CPU, right? So that would be a MIMD machine. But it turns out that we can also call this multi-threaded programming model single program multiple data, and it's multiple data for obvious reason because all these iterations are operating on different data, but also single program because the program is the same for all iterations. So this program is exactly the same as this one. It's exactly the same code, only executed by different threads. And the good thing of this single program multiple data programming style is that it can be executed efficiently on a SIMD machine, and that's a GPU. And that's why in the GPU context or terminology, we also call these single instruction multiple thread, because instead of writing with the idea of a vector processor, SIMD instructions in mind, we write code for threads. But these threads, as you will see, are going to be put together in some way in vector units or SIMD units to do the execution of single instructions. So SIMD, a GPU is a SIMD or SIMD machine. The difference is that it's not exposed to the programmer. The programmer doesn't use SIMD instruction. The programmer uses threads, and each thread executes the same code but operates on a different piece of data. So each thread has its own context. It might be started or paused or restarted independently, but the hardware is going to dynamically group the threads executing the same instruction to form something called a something called a warp or a wavefront in the GPU terminology. And this warp or wavefront is essentially a SIMD operation formed by the hardware. So you go write your code for multiple threads, let's say 100 threads, and you have these 100 threads or n threads, that is the number of iterations in the original sequential code. So you declare n threads. First thread executes this program. Second thread executes this other program that is the same program but operates on a different data. And then when it comes to running this program onto the hardware is going to take these threads and will say, okay, I have thread 0 that wants to execute this load. I have thread 1 that wants to execute this load. I have thread 2 and so on. All these loads are independent. All these loads are accessing the same array, so they are exactly the same load operation, but only the index or the stride changes. I'm going to put them together as if they were a vector instruction or a SIMD instruction, and I'm going to execute them on my SIMD machine. So that's essentially what we do here. Instead of talking about vector instructions now or SIMD instructions, we are going to talk about instructions that correspond to warps. What is a warp is a number of threads, a collection of threads. In particular, in NVIDIA architectures, is 32 threads. So it's a group of 32 threads that execute the same instruction at the same time, as if they were 32 vector lanes of a vector processor, right? So now the way that we are going to execute here is, this is one instruction for the different threads that resides in certain program counter X. Next instruction is program counter X plus 1, but as you see is also for warp 0, then the next instruction, then the next instruction. So graphics processing units are SIMD machines not exposed to programmer. We can see here what's the difference between SIMD and SIMD. SIMD is sequential instruction stream of SIMD instructions operating on multiple data elements. SIMD is multiple instruction streams of scalar instructions, because we are writing code for threads and one thread executes scalar instructions. But then they are later by the hardware grouped, these threads, to form the vector or SIMD instructions. There are two major advantages of SIMD. The first one is that we can treat each thread separately. I could write a program for a GPU with 100 threads, and each thread operating on completely different arrays, performing completely different operations and so on. and I could execute that on a GPU. Probably the performance will be terrible, but I can do it. And this is something that was not possible or very difficult to do in conventional SIMD processors. As I said, the fact that I can do it doesn't mean that it's going to be efficient, but at least gives me more flexibility and gives me the ability to write more complex and longer programs as well than what I could write if I use SIMD extensions, for example, of an x86 CPU. And also another advantage is that in principle, the threads can be grouped flexibly into warps. And we are going to see examples of this. So for the first one, remember that I said before, GPUs are SIMD machines, but they are they also use fine-grained multi-threading. And here, when we talk about fine-grained multi-threading, we don't talk about multi-threading of the individual threads. We talk about multi-threading of warps. And what that means, we are going to assume that a warp is 32 threads. You already know that. And if we have a code with 32 K iterations, and we assign 1 iteration per thread, then we will need 1K warps. And what we do when executing the warps onto the SIMD pipeline, onto the GPU pipeline, what we do is interleaving the execution of instructions for the different warps. So for example, we can start the execution of this load instruction for warp 0, and then we execute the same instruction for warp 1 that is for the next 32 threads. And then this instruction may be for warp 20. This instruction, of course, warp 20 already executed the 2 previous loads. That's necessary for the correct result of the program, and so on, right? And what's the advantage of doing this fine-grained multi-threading? The same advantages that fine-grained multi-threading originally has, and we quickly reviewed them in previous slides. The fact that fine-grained multi-threading can be used to hide latencies of longer operations. So yeah, this more or less repeats the same idea, the definition of a warp and the way that the warps are executed in an interleaved manner onto the SIMD pipeline. As you see, we can take a closer look at this SIMD pipeline. These are the shader cores in this figure, but these are what we normally call GPU core. If you go to NVIDIA terminology, you will see that these are called streaming multiprocessors. By the way, at the end of this presentation, you have one slide clarifying all these different terms. And if you take a closer look at this SIMD pipeline, at this shader core, you will identify multiple program counters for the different warps, masks as well, because this is a SIMD machine, so we need to have a mask, a register mask as well. Here we have instruction cache, decode, and the scalar pipeline, which are the functional units or the lanes that execute the instructions for each of the data elements. And here you can see a little bit more details for each of the lanes. You can here see the corresponding registers, the ALU, and so on. And eventually, these threads executing on these lanes, on these SIMD units, these functional units, they will miss in the data cache, so they will have to go to main memory or global memory, well, that's the name that we usually give to the external of chip DRAM memory in the GPU context. And these accesses take long latency, right? Take long latency because memory is far away, and also we will probably spend a lot of time accessing data from memory because we normally use GPUs to compute significant amounts of data. We are not going to use a GPU for a vector addition of 100 element vector. So we will have these kind of misses very frequently go into the main memory. The good thing is that while we are going to the main memory for warp 1, let's say, or for warp 0, we can continue the execution of instructions from other threads here in this pipeline, in this SIMD pipeline, right? And also recall this slide. I think that this will start making more and more sense now. Remember as well that we could execute a vector instruction on one single processing element or multiple processing elements, taking advantage of the time-space duality. And we are going to do the same for warps as well. Now, replace in the slides of the first part of the lecture, wherever you had SIMD instruction, now write instruction of a warp, and you will have exactly the same picture. And now, instead of talking about vector registers and talking about, I think we had here like registers corresponding to lane 0, lane 1, lane 2, and so on. Now these registers are for the threads, so they relate to a certain thread ID. That is a thread ID that we use in our code, and these threads map or are executed on one of these SIMD lanes. And you also know this picture as well, this slide as well. Remember that here we were executing vector instructions. Now forget about vector instructions. Now think about warps. If we have a warp of size 32, we have 32 threads per warp, but now it turns out that we only have 8 lanes, we only have 8 functional units. We will schedule the threads in this way, right? First 8, next cycle other 8, next cycle other 8, and so on. But as you see, it's essentially the same idea. Now, how do we write our code? Because I said the code or the program is the same for all the threads, it's single program, but multiple data, right? Meaning multiple data, meaning that different threads access different data and operate on different input data and generate different elements of the output data, of the output array, right? So the way of doing this partitioning is by using the thread ID to index the data elements. And here you have a super naive example. Imagine that this is just like a vector addition where we are so we perform here the element-wise addition of these two arrays of 16 elements. Let's assume, for example, 4 threads per warp instead of 32. So what we would do is assigning this part of the input arrays to warp 0, this part to warp 1, this part to warp 2, and so on. And here, this guy here is thread 0, thread 1, thread 2, thread 3, thread 4, thread 5, thread 6, and so on. So in my code, I will have, whenever I need to access the blue array or this green array, I will say, okay, access the element that corresponds to your thread ID. So thread 0 accesses these 2 elements, thread 1 accesses these 2 elements from the 2 arrays. So as you see, it's also pretty simple to write the code for these threads that will be later executed onto the SIMD engine. So and here let me very briefly show you how how a GPU program looks. In the end, we cannot execute everything on the GPU. Remember Amdahl's law, so we still need to use the CPU. So we will keep executing serial or modestly parallel code on the CPU. At some point, we will call what we call a GPU kernel, which is the function that is executed on the GPU, and we will start the execution on the GPU. And if you look at this block here, what we are doing is launching a bunch of threads onto the GPU to execute the code that we have written for all of them, or actually for one of them, because it's a single program, right? And notice as well that these threads are grouped in some way. You might be thinking about warps because we have already talked about warps, but this is kind of an intermediate layer. It's a software layer, and we call this the thread block. And as you will see, this thread block may have a variable number of threads that the programmer defines, and later the hardware will decompose this thread block into as many warps as needed. So this is why this slide says that warps are not exposed to GPU programmers, because the programmer decides, writes the program for sure, the kernel, and then when launching the kernel decides how many blocks and how many threads per block it needs to use. So for example, this is actually one very simplified CUDA code or GPU code written in CUDA. As you see, instead of having a for loop that goes through all the elements of all the arrays, here we generate a, let's say, ID that relates to the block ID and the thread ID. And this way, every thread that executes on the GPU can address the corresponding elements of the corresponding input arrays and output arrays. And here you have more or less the same code, but here is not so much simplified. And you see here, this main would be the host function, the main function that executes, runs on the CPU. At some point, it will call the add matrix kernel, and this is the add matrix kernel that runs on the GPU, right? And as you see here, we have two inputs, A and B arrays, and we are obtaining certain, in this case, it's a two-dimensional computation, so we are obtaining some index from the indices of the threads and the blocks that we use. But this lecture today is not about GPU programming. If you are interested about GPU programming, you can take a look at this lecture from last year, or you can also take a look at our Heterogeneous Systems course that we are teaching every Thursday at 7 p.m. Actually, we have one new lecture today, and as you see, all the materials are available in our website and in YouTube. And now, remember that I talk about the blocks, and what's a block? In the end, a block is just a software invention, right? It's a programmer that says, oh, I want to group my threads into groups of, let's say, 128 threads or 1024 threads. And that's what I call a warp. But now when I start the execution of my program, my kernel onto the hardware needs to decompose these blocks into smaller things that are understandable by the hardware. And these smaller things are smaller groups of threads that are called warps. And these warps contain 32 threads, as you know. So this might be one warp, and the warp is like divided into threads of 32, so into warps of 32 threads. We can compare this warp-based SIMD execution with the traditional SIMD. And the traditional SIMD, we have a single thread, sequential instruction execution. Instructions are executed in lockstep. All registers or all lanes go at the same one. The programming model is not SIMD. Sorry, the programming model is SIMD because we are not using more than one thread, but we use vector and SIMD instructions. In the case of the warp-based SIMD, we can treat all threads individually. We don't need to worry about the vector length. In the end, the software, the programmer doesn't need to know that the warp size is 32. You could write a CUDA program without having any idea about what's the meaning of a warp, and your program would work because the ISA is scalar and you write code for individual threads. And and this is essentially the way of implementing a SPMD programming model on a SIMD machine, on SIMD hardware. SPMD, as you already know, a single procedure or single program, multiple data. It's a programming model, not a computer organization. And we have multiple threads, or if you want to call them procedures, they are like different procedures, and these different procedures, these different threads can also communicate. Don't think that they are completely independent of each other. They can use barriers to synchronize. If you take a look at the GPU programming lectures, you will understand how to use these barriers. And yeah, all these threads execute the same instruction stream, but work on different data, and they may have also different control flow paths. There is no problem. The hardware will be able to handle these divergence of execution if they follow different control flow paths. And yeah, so I guess that must be clear so far. We are going to see more about the advantages of SIMD. The second one is that we can group threads into warps flexibly. Think about, I was talking about the divergence in the control flow path. Imagine you have like a very convoluted code like this one here with different basic blocks, and and different if-else statements, so that, for example, this thread 1 follows this path, thread 2 follows this different path, thread 3, thread 4, and so on, right? And the problem here is that these 4 guys belong to the same warp, so they have the same PC. How is the hardware going to handle this divergence that the programmer needs in the program, in the execution of the program? Well, the idea to handle this divergence that we normally call warp divergence or branch divergence is by using predicated execution in the same way as we saw in the SIMD part of the lecture. We are going to generate masks for those threads that satisfy the condition that is required to execute path A. We will first execute path A with the corresponding mask, then we can complement the mask or maybe recalculate a new mask depending on the conditions in order to identify those threads that will execute path B, and they all execute, and the program will perform correctly and will produce correct results. Now the point is, but you have like idle threads here, right? Yes, you have them, and if you have the idle threads, your performance goes down. But and that's something, one thing that we teach in our GPU programming lectures is how to rearrange the computation, how to write our programs in a different way in order to minimize this amount of divergence and increase the performance that we can achieve. So as you see, a naive program will work, will produce correct results, but it won't be the best performance because it's not optimized. In the worst case, you will have some divergence, but there are always many different ways of reducing the divergence. So one other thing that I want to discuss right before we finish the lecture is that these threads could potentially form the warps flexibly. It's not the case in real GPUs, where we know that you have a thread block of 128 threads, so that corresponds to 4 warps. The first 32 threads go to warp 0. The next 32 threads from thread 32 to 63 go to warp 1, and so on. But one thing that we could do is, for example, merging threads from different warps and creating new warps that are going to be more efficient. For example, I have these 2 warps. You know that these 2 are incomplete because some of the threads are idle, but it turns out that the lanes where they will be executed are not the same, right? So we can clearly put one on top of the other and create a new warp that is hopefully going to be more efficient. And that's what this paper proposes, performing these merging of incomplete warps in a way that you can obtain more performance, in the end, less execution cycles. So you have a simple example here in the baseline where you see that it takes a long time to execute the whole program because there is a lot of divergence, while this dynamic warp formation proposal finds ways of merging 2 warps together. As you see in this case, C and D are merged, and this can be executed much faster, or these two warps in the F basic block, they can also be merged together, be executed much faster, and this way save a significant amount of time. One question that you may ask yourself is, do I need to, have, for example, here, non-overlapping threads? Yeah, in principle, that's a requirement for this dynamic warp formation technique. There would be, I don't think it's impossible to move, let's say, for example, here where we have 2, so what is it? Like here, these 2, we cannot merge them because they overlap, right? They fall on the same functional unit, on the same lane. Well, could we kind of move one thread running here to a different lane? Yeah, we could, right? But it would be costly as well because we would need to move all the registers from, or at least a few registers from this lane to another lane. it's not impossible, but probably would require significant hardware changes. So you always have to evaluate trade-offs when you come up with some new idea for optimizing your hardware. A related or similar approach is also coming from this paper that not only proposes, better ways of creating the warps, but also better ways of hiding the latency operations, like the accesses to main memory. For the branch divergence idea, so for the divergence idea is, it kind of resembles the previous idea, but in this case, it's kind of creating large warps from smaller warps. So for example, imagine that here the warps are of size 4. So this is let's say the bit mask for warp 0, this is the bit mask for warp 1, this is the bit mask for warp 2, and so on. So this mechanism detects different non-overlapping threads, even though they belong to different warps, and creates let's say a sub-warp. Actually, it's the other way around. These are not different warps. This is like a larger warp. In this case, let's say 128 threads, and it creates a smaller warps from the larger warp. And this sub-warp would be, for example, of 32 threads, right? And now it detects another sub-warp and start the execution of the sub-warp and so on. And then regarding the access to memory, how to reduce the long latency, so how to hide the long latency operations better. One thing that the authors of this paper detected is that in the typical round-robin scheduling that is normally used in GPUs, we are going to have situations like this. All threads from all warps are computing. Remember, or load, add, mul, store code, simple code. There will be parts, parts of the computation where all threads are computing, right? Like, for example, they all are in the add instruction, they all are in the mul instruction, but at some point, all of them will have to execute a load or execute a store. And the problem is that these accesses will start at different times, but at some point, they all will overlap. And that's something that really makes sense, right? Because if the programs are the same for all the threads and for all the warps, it's normal that at some point all of them will have to go to the global memory, and there may not be more compute instructions to hide the access to memory, right? And that's what happens. We will still see long gaps where we cannot hide the long latency operations. So what the authors propose is dividing the total number of warps into different groups, in this case, 2 groups, and start doing this round robin, but internally in each of the groups. So for example, if you had here 32 warps, now you divide the 32 warps into 16 and 16. So first execute the compute instructions for the 16, and then start requesting accesses to the main memory, the global memory, while at the same time we are still hiding some of this latency thanks to the fact that we are now scheduling other threads. And here you see how many cycles can be saved. Okay, we are very close to the end. I still have 30 more minutes to take a look at the real GPUs. And I think that this is hopefully will be completely clarifying with respect to the connection between SIMD processors and GPUs. This is one of the oldest compute capable or CUDA capable GPUs from 2008 as a GTX 285, as you see, with 30 cores, 30 GPU cores, or 30 streaming multiprocessors. If you take a look at the internals, you will see something like this. Observe that there is an execution, context, storage, instruction stream decode, and then we have the SIMD functional units that contain multiply, add, and other functional units as well. It can execute groups of 32 threads that are the warps. There is, of course, a limitation in the maximum number of warps that we can have in each core, because in the end, the number of thread contexts, PCs, masks that we have is limited. But yeah, it was really powerful at its time. Like you see, could run more than 30K threads at once on the system, right? But over the years, over 11 years that GPUs have increased their performance and the number of functional units, and also their energy efficiency, by the way, significantly. And you see like much more powerful from, I don't know, like this is like maybe 200 functional units to we are in almost 7,000, right? So you see how the processors have improved. In 2007, this Volta V100 architecture was released. This architecture was very special for NVIDIA because you see up to 80 cores here. But if you take a look at one of the cores, you will see one of the key differences in this core is that they have these kind of tensor cores that are optimized for deep learning, for machine learning workloads. But that's not the most important thing in this figure. What I would like you to check now is that we have here different compute units or different execution units or functional units. Observe how we have units that are specialized for FP64, so double precision, here integers, here floating point 32, here we have load and store units, and here we also have these special function units that execute transcendental operations, right? Like for example, sine, cosine, etc. So as you see, we have different types of processors, different types of execution units, same as in a vector processor, but also if you count the number of units that we have, you will see that it's not 32. In some cases, it's a lower number, right? So for example, here we have 1, 2, 3, 4, 5, 8. So we have 8 load store units for every warp. What that means is that here we will have to pipeline the execution of the threads in the warp. We will first start the execution of the load operation for the first 8 threads. Then we, one cycle later for the next 8 threads, one cycle later for the next 8 threads, and so on. What is clear here as well is that the instruction won't be completed, the instruction won't retire completely until the operation has been performed for the 32 threads of the warp. I think that is obvious. But you can see here the combination of vector and array processors, and you can also see here many more concepts that we have covered in the lecture. For example, you have a memory space here that is called the shared memory. This is a banked memory as well. And actually this is interleaved in a kind of naive manner. So it's very frequent to have bank conflicts in the access to this shared memory. That's also something that you can watch in our GPU programming lectures, where we talk about how to deal with these bank conflicts as well and try to minimize them from the software point of view. And now, if you want, we can take a closer look at the this tensor core and the internal of the V100 core. As you can imagine, there's not much public information about how this is built internally. But for example, in this paper, they tried to do some sort of reverse engineering, micro benchmarking to understand how these tensor cores are built. In the end, these tensor cores that are, as I said before, optimized for execution of machine learning workloads, and essentially a key operation in machine learning workloads is the dot product operation, multiply and accumulate. So that's essentially what these guys do, and do it very, very efficiently. Actually, if you compare numbers here, is like essentially 1 order of magnitude faster than the regular cores in the best case. So one thing they realized, the authors of this paper realized, is that each warp uses 2 tensor cores. Each tensor core contains 2 octets. And inside the octets, we have 16. So we have SIMD units, 8 SIMD units per octet. So in total, 16 SIMD units per tensor core. And one SIMD unit looks like this. As you see, it has 4 inputs. So here we perform the dot product operation of 4 input values. So each of the SIMD units computes a 4x4 matrix multiplication, and can do it essentially in one cycle. So that's extremely efficient, because also we have many of these SIMD units. So that's why GPUs are most modern and powerful GPUs are so good at machine learning workloads, because they have these units to execute dot product and matrix multiplications in an extremely fast manner. But in the end, it's nothing but a SIMD unit similar to the concept we have described in this lecture. There is, I would say, the most particular thing about these tensor cores is that instead of having a partition register file and each thread, each lane accesses only its own registers, here the threads are not anymore private to each thread, and they can be shared inside all the threads of the warp. And that's necessary to use these SIMD units efficiently to perform the matrix multiplication. As I said, these tensor cores were designed for machine learning workloads especially, but they are not the only specialized processors for machine learning that you have seen in this course. Geraldo, a couple of weeks ago, presented the Mensa work that is an analysis of Edge TPU, the tensor processing unit from Google, that it's essentially an accelerator, a spatial accelerator for machine learning workloads. And in particular, this accelerator follows the systolic array model, where we have a two-dimensional array of processing elements that receive data, from two of these sites and perform a matrix multiplication very efficiently, as well as Gerald explained. And you can take another look at this talk. Here you have the link to the corresponding lecture. But as I also said before, you can also watch Professor Mudlu's lecture on systolic arrays. And more recently, regarding NVIDIA GPUs, the A100 was launched last year. Essentially the same idea as the previous generation, but now more powerful, more support for machine learning workloads, even some support for sparsity. It's even a larger die with more cores, 108 cores in the most powerful GPU so far. But if you take a look at the internals of the A100 core, you will see that it's also quite similar to the V100 core. The main, one of the key differences is here in these tensor cores, that now they have some way of doing, pruning, of getting rid of some of the weights, and this way save multiplications and have more efficient execution. So yeah, this is almost everything for today. Just a little bit of food for thought, and then I hope I can take some more questions. You can by yourself compare and contrast GPUs and systolic arrays, the difference between SIMD machine and a MISD machine like the systolic array. You can think what is better for the different workloads that you may have in mind for machine learning, for image and vision processing, and think about the types of parallelism that each one exploits. I think that we have talked a little bit about that today. What are the trade-offs of each of them, and think as well whether it makes sense to combine these two concepts or these two paradigms into the same processors. I believe it makes sense, and I think that there are also kind of some modern architectures that are starting to do this, and maybe in a future edition of this course we will talk about them as well. But as I said before, if you are interested in learning more about GPUs, you can take a look, for example, at this heterogeneous systems course. There you have the links to your YouTube channel, and also or playlist, and also the link to the website, where, as usual, you will find all materials that we are using in this course. So that's all from me for now, unless you guys have any questions. Or are there any questions in YouTube?
Yeah, I actually have a question. So all these architectures you presented here were all for these sort of general purpose GPUs. But how does this architecture differ from before they were made general purpose, when they were just for graphics processing? Yeah.
Yeah, it's essentially the same architecture. It's actually, I don't remember exactly, but CUDA means compute unified device architecture, if I recall correctly. So this unified means that the same hardware is capable of both executing code for graphics and general purpose code. And actually, if you can put it this way, GPUs started, like I would say, I don't remember exactly, but at least 25 years ago, they started as specialized accelerators for a particular type of workloads that are computer graphics, right? Now the point is that at some point, let's say 15 years ago or so, some researchers started to realize that they could use that massive amount of compute power to do more computation, right? Because in the end, when you create graphics, you are creating pixel by pixel, and you are performing operations on all these different pixels at the same time, because you have a large array of execution units. And someone thought, okay, what if instead of mapping here, like the pixel values or the different channels, RGB of the pixel, what if I map A0, A1, and A2? And then I execute a vector addition, or I execute a matrix multiplication. They tried, it worked very well, very good performance, very high energy efficiency. And then it was time for industry vendors to really enable this general purpose computing on the GPUs, right? So now put it the other way around. Imagine that you have something as complex as a current GPU these days. Can you execute a computer graphics workload on this architecture? Can you do it in an efficient manner? Yes, you can. Make sense?
Yeah, yeah. Okay, so I guess all they changed was they made it easier to program, pretty much. Because I guess before you just had to rely on writing shaders
Yes.
for like OpenGL, and it was horrible. And now
exactly. Writing a matrix multiplication with OpenGL is much more difficult than doing it with CUDA. So essentially, what they did was creating the programming framework and extending the hardware minimally, I guess, to support all these new operations that now we needed.
Okay, makes sense. Yeah, thanks.
Yeah, thank you for the question.
I had a question.
Yes.
Not necessarily related to this, but about the exam tomorrow. A while ago, you said you'd give us more information a few days before the exam. The exam is tomorrow. So how do we know which room we go to? Because there's two of them, and they're completely opposite on like all sides of the building. So it's going to take a bit of time to go between them for 1250.
Yes. We are going to send an email a message today. It's essentially half of the students will go to one room and the other half will go to the other room. You can even, I don't know if you have there is a public list of the students taking the exam, but yeah, you can even infer what's going to be your room in advance. But yeah, essentially we're going to take the list. Half of the students will be assigned to one room, the other one to the other room, because also you are not too many people. So I think that we can easily find a place for all of you very quickly. Just make sure that you are there in the examination room like 5 minutes before the start of the exam. We will open the doors and we'll let you in, and you will find a seat with safety distance and so on. Don't forget your face masks for sure. And yeah, that's essentially everything. But yeah, thank you for the reminder. We will give you this information later today. Anything else? Okay.
Nothing on YouTube. So
okay. Fine. Yeah, thank you very much, everyone. Thank you for your attention. I hope you found this interesting. I hope everything was more or less clear. If something is not clear, please ping me. I will be glad to clarify anything. And if you are curious about GPUs and also other types of heterogeneous processors or heterogeneous systems, please take a look at this course, same as all or other PNS courses that relate very much to these master's course. As you may know, we also have PNS courses on processing in memory, on genomics. We also have on DRAM systems or memory systems. So probably the materials that we cover in these courses can also be interesting to you. Yeah, thank you very much again for your attention, and I'll see you tomorrow.